Hello, this video is the continuation of previous video regarding the preparation and properties of ether. In previous video, we have started talking about the um, preparation or synthesis of ether by using Williamson's ether synthesis, in which we react alco oxide with alkyl halide which undergo SN2 type of reaction and will give ether, and will leave X or halogen as the leaving group. And we mentioned that for this type of reaction we obtained alco oxide from alcohol. Obviously, alcohol oxide is obtained from alcohol by reacting with a very powerful base such as sodium, or we could use potassium, or we could use like a sodium hydride. You can use any one of these: sodium, potassium, sodium hydride. The result will give you alcohol oxide. And this alcohol oxide, say, if you use sodium, sodium alcohol oxide; if you use potassium, potassium alcohol oxide, and so on and so forth. And this alcohol oxide we can react with alkyl halide. Now, say for example, if we have something like CS3 CS2OH ethanol. When you react with sodium, it will give, like, say, CS3 CS2O minus sodium ethoxide, okay, and Na will go with sodium, so sodium ethoxide. Now this sodium ethoxide CS2O minus and Na plus, you can react with any alkyl halide, say for example CS3Br. Then it can undergo SN2 reaction very easily, resulting in the formation of CS3CS2O, and here is CS3, and bromine and sodium goes together, resulting in giving you sodium bromide. Now, in this category you may see the question, say for example you have some type of alcohol, okay, and we are reacting with, say for example, number one, say sodium hydride, and number two, you are reacting with some kind of alkyl halide, CS3 CS2 CS2 Cl. Then you need to draw what is the product that will form. So what you need to understand is the sodium hydride here is to deprotonate this hydrogen, and first, in step 1, first of all it will generate alcohol oxide, sodium alcohol oxide. So cyclohexane O minus, and you can put Na plus next to it. Now this alcohol oxide, then it is ready to react with, say, this alkyl halide. Now here is, in this case, the second step, that is CS3 CS2 CS2 Cl. You can do SN2 reaction very easily, and the result is the cyclohexane ring, oxygen, and you have CS2 CS2 CS3. That will be your product. And of course sodium and chlorine goes together to give you sodium chloride. We can have varieties of questions related to that, so you need to be very comfortable with that. Now here is one very important point to be noted. If you have some kind of alcohol, ROH, we have to, in order to, you know that the pKa of alcohol is nearly 16, so it is a very weak acid. Therefore we have to use either sodium or potassium or sodium hydride as the base in order to deprotonate this. But if we are using, say for example, aromatic alcohol, or we can also call that as phenol, right? In And you know that phenol has pKa very close to 10. So because of this more acidic nature of this phenol, in order to deprotonate that, we don't need to use such a very powerful base. We can use the strong base like sodium hydroxide. sodium hydroxide will able to deprotonate that, resulting in the formation of phenoxide. O minus, it is called phenoxide. Of course, sodium will go next to it, sodium phenoxide, but it will result. Be careful. This is with the phenol only this happens there, phenoxide. Okay, it has to be the aromatic ring. And now you can do the SN2 reaction. Say for example, CS3O OTS, you can make the leaving group, right? Alkyl halide or any good leaving group can work, and you can have kind of SN2 reaction that can result in the formation of ether as well, OCS3. In this case, I'm using tosylate as the leaving group. You can use CS3Br also. Okay, so that is how we do the SN2 reaction on when you have the phenol ring there. Now, the next way to prepare this ether is by alkoxymercuration demercuration. The other method of preparing ether is by alkoxymercuration, demercuration. So again, remember this alkoxymercuration demercuration is this is the reaction of alkene. So say for example, if you have the unsymmetrical alkene and you want to add water across the double bond, you can do the hydration reaction, and that is called oxymercuration demercuration. And the reagent for this is you have number one, mercuric acetate, and you are of course adding water, and the second step you need sodium borohydride for the deprotonation. And in this case you are adding what? Hydrogen in one carbon and OH in the other carbon. This is called oxymercuration, demercuration. Okay, so sodium borohydride is for demercuration. This is called oxymercuration, demercuration. And this will give the add water across a double bond by using what we call the Markovnikov rule. Markovnikov's rule. And very similar to this method, but if we wanted to do alkoxymercuration, instead of water we are adding alcohol. Okay, and the reaction occurs very similar to that. It's called mercuric acetate, and instead of water we are adding alcohol, ROH, and hydrogen will add to one carbon, RO group will add to the other carbon. And demercuration is same as previous. Okay, NaBS4 is for demercuration. The resulting result is hydrogen will add to one carbon, whereas RO or alkoxide group will add to the other carbon. So this result in the formation of ether as the product. So this is the reaction called alkoxymercuration demercuration. And again, addition of alcohol takes place by Markovnikov rule. And you know that in case of alkoxymercuration demercuration or oxymercuration demercuration, there is no rearrangement. Okay, this will prevent from rearrangement. No rearrangement happens there. So that is how we can prepare alcohol. Say for example, now we have some type of like a unsymmetrical alkene, like this is an unsymmetrical alkene, and you wanted to convert this into, say for example, you have um, uh, oxygen is here, and we have some kind of, say for example, four membrane. This is the ether that you wanted to prepare. Now the question is, what is the reagent that you wanted to use? Now for this, again, if you have the idea about alkoxymercuration, demercuration, we can easily achieve this. So what you need to think is, across this double bond, we have added hydrogen to one carbon and then this alkoxide group to other carbon. So that is how you should able to achieve this. So the first step is we need to do alkoxymercuration, but be careful, this alcohol that we need is, this is the RO, right? RO. Our R group is four-member ring with the OH. So this is our ROH. And second demercuration is, of course, sodium borohydride. So that is how we can easily obtain the desired product depending upon what we wanted to add. Now, in this connection, actually, now, for example, sometimes if we cannot figure out what alcohol should we use and how we should proceed, actually, this we can achieve in other way also. Say, for example, I would do this. Okay, for example, I wanted to go with just oxymercuration. HgOAc 2, and we want to add water, and in second step sodium borohydride. For example, if you cannot figure out the alcohol at this point, we can do this also. Okay, and for the same result we can do other approach. That is what we are discussing here. First of all, this will add water. Okay, hydrogen here and OH here. Now our interest is to get this kind of ether. So what we need to do is we wanted to deprotonate that, say for example using sodium or potassium or sodium hydride, that Williamson synthesis that we discussed before. So that will result in the formation of alkoxide and sodium alkoxide, say for example. Now we have to add four-member ring here, so that is when we have to use this with some kind of leaving group, say with the bromine there. Okay, and then we can easily do the SN2 reaction that will result in the formation of desired ether. So hydrogen we may write or we may not write O, and this is where you have your now four-member ring is connected. This is how you prepare your ether. So that is the alkoxymercuration demercuration reaction. Now there is one other methods to prepare a simple ether, and that is we can also consider as the industrial method of ether preparation. That is called bimolecular dehydration. Bimolecular dehydration, and this is actually we consider that as the industrial method of industrial ether synthesis. If since we need a ether in large scale for the industrial purpose, we can use this method. So in this method, bimolecular dehydration means, suppose you have ethanol, two molecule of ethanol. So I will write this way here, CS3 CS2OH, CS3 CS2OH. If we do the dehydration, you remove the water molecule, say for example like this, dehydration. Now, in order to do this dehydration, you need the concentrated sulfuric acid, and you got to heat around 140°C temperature. Okay, and then this dehydration will take place, and you will get diethyl ether plus water is the side product. But here, this method is very appropriate for this kind of what we call is symmetrical ether. Symmetrical means you have both sides, this ethyl group. So this type of ether, this is called symmetrical ether, we can prepare by this kind of method. It's a kind of cheap and very easy to prepare large scale synthesis. But however, there is a, if you need the mixed ether, cannot be synthesized, cannot prepare by this method, because in this case In this case, in the